This is Andy Barrett of polyphys.com, and I'll be introducing an app I made that allows you to explore the behavior of charged particles in a many-body system. All of the particles here are pushing off of each other with a force that follows an inverse square law with respect to separation, and all of the charges and masses of the particles are the same. At every frame of the simulation, an acceleration due to Coulomb's law is calculated. If that were the end of it, then they would all just fly apart. So in order for us to study the behavior of particles under these conditions, we need some way of confining them in order to hold them all together. We do this by applying a central force that pulls every particle towards the origin. The magnitude of the force that each particle experiences is proportional to how far away it is from the origin. The equation for the magnitude of the force can be seen up here on the top right. R is the radius of a particle from the origin, and the force is proportional to the radius raised to some power. The power p and proportionality constant s can be adjusted over here. Also, the green curve on the plot to the left shows the force as a function of radius. The third force that these particles experience is drag, which acts like a sort of friction, causing them to slow down and eventually come to equilibrium, as you can see here. Drag can be controlled by this coefficient. When the drag coefficient is very high, particles move as though they're in a very viscous fluid, which resists their motion. The result is that particles slow down over time, as though energy is being sucked out of the system. When we set the drag to zero, we might think that the particles will behave in a Newtonian way, like billiard balls which scatter off of each other. But in reality, the simulation becomes unstable as self-amplifying numerical errors arise. So we actually need this drag to make this study possible. Beyond that, we can use the drag as an actual physical parameter to study how it affects the behavior of the system. One example that I'll give is this. When you start with the system in a highly random state and increase the drag, it will relax to a very disordered, solid structure, kind of like a glass. Though the kinetic energies are all zero here, we know this isn't the true low energy state, because all of the force functions have complete angular symmetry, and so we expect the relaxed system to look like a hexagonal lattice, simply for mathematical reasons. So let's see what we get. At this stage, it looks like the glass liquefies. We can see planes of particles starting to slide past each other as the system equilibrates into a hexagonal lattice, as indicated by crystal planes at 60 degrees from each other. So this is the physical use of the drag coefficient. We can use it to tune how fast friction sucks kinetic energy out of the system, and this allows us to take something like a gaseous system and cool it down into a solid. So then what we just found is that we get a more crystalline structure if we allow the system to cool down slower, and this is actually how reality behaves. Regarding the drag coefficient threshold for this phase transition, there are some isosurfaces with respect to the other settings, but there are 1,000 things I could say about this app, but I'll leave it to you to play with it. I will say about the plot on the left that the red curve corresponds to the radial density distribution of particles, so averaged over angle. We can see that when the system has come to equilibrium, these peaks form, with the rightmost peak corresponding to the outer ring of particles, and each peak to the left of that corresponding to the concentric rings of particles within. The blue curve shows the angular density distribution, from 0 on the left to pi on the right. It doesn't show anything now, but sometimes the crystal planes are evident in this plot. Well, that's all I wanted to say about this app for now. Please go to polyphys.com to check out this app and many more. This is really a labor of love for me, so if you've enjoyed these apps, then please consider making a donation so that I can keep this project growing.